Thanks to the entire organization committee for the opportunity to talk here today. Yeah, my name is Kufner. I'm currently a postdoc with Dimitar Sasolov, and my research focuses on how UV light has affected the formation of prebiotic building blocks. And today I'm going to speak about the photochemistry specifically in prebiotic lakes. In the first half of my talk, I'm going to focus on the photochemistry or the penetration depth into prebiotic lakes specifically. And in the second half of my talk, I'm going to speak about the photochemistry, like the actual chemistry that can go on in these lakes. So if we think about the origins of life as in a planetary context, like on early Earth or in an exoplanetary system, we always need a driving force. This can be a disequilibrium of a pH gradient, wet-dry cycling, day-night cycling, hot-cold, pressure gradients. So among all of these, there are scenarios like lake scenarios where we would look at a lake on the surface of the early Earth, for example, which cover a variety of these disequilibrium conditions. So this is what I'm going to focus on today. But also, if we consider a lake scenario on the surface of a planet such as early Earth, there is one additional ingredient, and this is UV light, which is an important energy source and can be driving force for many photochemical reactions. So one big question is, how deep does the UV light from the sun actually penetrate into prebiotic lakes? And this is a question that strongly depends on the salt constituents that we have in such a lake scenario, also on the atmospheric gases, but I'm really going to focus on the liquid today. So what we did was actually we reached out to several research groups in the field and asked them about salt constituents in early lakes, and started, based on their replies, making a catalog of various different salt constituents that could have been present on early Earth lakes in such a scenario. And this plot here on the left shows an example of spectra from 200 nanometers to 320 nanometers on the x-axis. And the y-axis shows the extinction coefficients on a logarithmic scale. And this shows only a few of the salts, specifically the N ions. But what we mainly found was that most of the salt constituents are deep UVC absorbers in the range between 200 and 220 nanometers. But a few of them, and specifically the iron-containing samples, such as ferrocyanide, actually absorb way further into the UVB or even UVA range. So it really depends on what salt constituents are present in an early lake or also on an exoplanet lake, how deep the UV light can actually penetrate into the lake and cause photophysics. Someone's not muted. Okay.
I think that's you, Tony Jha.
Okay. Thank you. So as another example, if we take such a scenario, and this is not claiming a specific salt composition of a specific lake on early Earth by any means, it is just an example basically offering a tool to calculate which salt constituents allow for which penetration depth. But if we do that, in this example for a freshwater lake with chloride, bromide, and iodide at specific concentrations, we end up getting a solar irradiance on the surface of the early Earth, which is shown in black, that actually gets attenuated the further it penetrates down into the lake. And specifically with the absorption being higher at low UVC wavelength, the deeper it penetrates, the more of the deep UVC light is attenuated. So we get a spectral dependence and a depth dependence at the same time. So in simple words, this means that particularly short wavelength UVC light rather gets attenuated at lower depth, and at higher depth, the longer wavelength UVB radiation is actually able to penetrate deeper into the waters, and both can there induce different kinds of photochemistry. Another example is a simple lake that is rich in sulfite, for example, high sulfite concentration, and that would have a small concentration of DNA or RNA oligonucleotides, for example. In such a scenario, sulfite would be the main absorber between 200 and 250 nanometers. So the short wavelength UV light would be absorbed immediately under the surface and would actually eject solvated electrons from the SO3 2-. So we get a layer where we would have a lot of electrons in solution, and longer UV irradiation above 250 nanometers would actually be able to penetrate deeper into the lake and there initiate other photochemical reactions. So as announced earlier, I'm going to talk both about the penetration depth, but also about the photochemistry that can be going on in such lake scenarios. And this is what I want to spend the rest of the time in this talk on. So sunlight as an energy source is able to activate photochemistry. But in this role, it has an ambivalent function because it can both interrupt chemical reaction networks, but on the other hand, it can also act as a driving force to do productive photochemistry. And the latter is something that I want to highlight here and show it on a very prominent example reaction that is self-repair by UV light of short oligonucleotides. So what we're looking at here is a short DNA sequence that gets damaged by a UV photon, and the most abundant UV lesion induced by deep UV light is a so-called cyclobutane pyrimidine dimer, which is a cyclobutane ring that essentially forms between the C5 and C6 atoms of two neighboring pyrimidines, in this case, two thymines. So this lesion is fortunately photoreversible. So if we shine another UV photon on it, there is a small chance that it gets reverted. However, what works even better is excitation of the direct neighbors. In this case, if we excite the guanine neighbor, then there is a chance of a charge transfer between the G and the A, and an electron can hop into the lesion, cleave the lesion, and recover the intact sequence. Now, this process is highly sequence selective. So if we replace one base like the adenine in that sequence by cytosine or thymine, that entire self-repair process does not work anymore. And we went further and studied the mechanism as to why that is with a setup that is called ultrafast pump probe spectroscopy. And the principle how it works is that we excite a sample with an ultra short UV pump pulse on the order of a picosecond. To give you an idea, a picosecond compared to 1 second is about like a couple of days compared to the age of the universe. So ultra fast on the lifetime scale of molecules. So with this method is actually something where we can observe photochemical reactions in real time, watch the molecules as they react. Where the excitation essentially causes the molecule to go from its ground state, here shown as a 0, up to an electronically excited state, like the pi start state here. From there, the molecule can actually decay directly down to its ground state again, or it can go through an intermediate charge transfer state. And what we then do is we send in a second pulse, a probe pulse, in this case, an infrared pulse, but we also have a capability of doing that in the visible in our lab. And this allows us to monitor the population of the ground state and of the charge transfer state very distinctly. So what we do is we actually tune the arrival time of the pump pulse and the probe pulse to monitor the photochemical reactions. And this here shows an example of how this is done. So the plot shows the spectral line of the guanine ground state at 1576 wave numbers. So that is a line that shows the population of the G ground state. On the x-axis, you can see the delay time. So that is the delay between the arrival of the pump and the probe pulse. And on the y-axis, the change in the absorption signal. So what happens at time 0 is that we send in a pump pulse, which depletes the ground state. So we get a negative signal, which then slowly recovers, or relatively speaking, recovers back to the ground state. And that happens on different time scales. So all of these dinucleotides go through a charge transfer state. But in case of the GT and the GC, that happens really quickly on the order of tens of picoseconds. Whereas for the GA dinucleotide, that happens on the order of hundreds of picoseconds. So the GA, or in the case of the GA, the energy is stored much longer in the intermediate charge transfer state than in case of the GC and GT. So to give you an idea how an entire data set of such an experiment looks like, here are the 3D color maps of those 3 samples. And the line that we've just been looking at 1576 wave numbers is the left blue line. So on the x-axis is shown the wave numbers, and on the y-axis, the delay times. So in this coding, negative lines mean, or blue lines mean negative lines, a bleaching line, and red means positive lines where a new species forms. So in case of the 1576 nanometer line, you can see it as the left blue line in case of the GA, or also in the GT case. For GA, that line stays way longer than in the GT case. And additionally, we observe red new species, which correspond to the charge transfer. So the G radical cation or A radical anions, or T and C. Below that, these are results from a global fitting analysis, which corresponds to the specific lifetimes of the charge transfer state. And on the bottom line, that shows stationary steady states, FTIR spectra. I'm not going to speak about that in detail unless you have further questions, but this is to give you a general idea of how these data sets look like. But the main message that we get out of it is in case of the GATT, where we see a strong self-repair activity, the electron actually has 300 to 400 picoseconds to get transferred into the CPD lesion and open it. Whereas in case of the GC or GT, that intermediate state only lives for about 20 picoseconds, which is just not enough time for the electron to get transferred into the lesion and repair it. So that explains the mechanism behind that sequence selectivity. But in general, the application of that strong sequence selectivity is that some short oligonucleotides, DNA or RNA, are just more likely to survive solar irradiation under early Earth conditions than others. So with this, I would like to end, and I would like to thank the team at Harvard who were involved in the penetration depth project. And I would also like to thank the team in Munich with the pump probe experiments of the second half, the funding agencies, and specifically you for your kind attention.